Hey everybody, Scott Roberts here from Explore Scientific, and today is Astronomy Day. Early on today, I was on Woodland Hills Camera and Telescope on their YouTube feed, and we gave away this eyepiece, a 25 millimeter 100-degree eyepiece. We'll be doing more shows like that in the future, both with Woodland Hills and with some of our other dealers, hopefully, and also through Explore Scientific as well. It's always fun to give a door prize away, but this time, since we already gave away a door prize today, we'll save that for a future time. But today I wanted to talk to you about eyepieces and how to choose and use them. Explore Scientific makes a wide range of eyepieces. We have over 40 different models in 7 different series, ranging in prices from about under $80 to over $800, depending on what you're looking for. But when you match your eye to the eyepiece and your telescope combination, you get the best possible visual views. It also depends a lot about your seeing conditions as well. And so a while back, and you'll be able to see a younger Scott Roberts giving a video presentation, but I'm going to switch to that program, and I will walk you through how to choose and use eyepieces, which can be applied to any eyepieces out there. One of the things you'll learn about Explore Scientific eyepieces, though, is that we have a forever, no fault, transferable warranty. So if this, if this eyepiece burns to the ground somehow, and you can gather up its remains and send it back to us, we'll replace it at no charge. That's our deal. That's how we stand behind our eyepieces. So, I think that if you get a chance to go out to a star party and share the eyepiece with someone, you'll be able to see what Explore Scientific brings to the game. Thanks very much, and I'll be back here in a few minutes to talk more to you live. You're at the Explore Scientific Customer Service and Training Center, and we're going to learn how to choose and use eyepieces. Modern design of telescope eyepieces have revolutionized visual astronomy with breakthroughs in computer optimization and new optical glasses. Today's top eyepiece manufacturers design high-performance eyepieces with superior edge performance with a wide range of apparent fields and long eye relief. So how do you choose? Today there are many premium quality eyepieces to choose from for your telescopes. But with so many focal lengths and a variety of apparent fields of view, how do you choose what's best and what fits you best for your specific telescope? Here are the eyepiece selection considerations. We're going to find out the lowest useful magnification of your telescope, the highest useful magnification, how to choose eyepieces between lowest and highest useful magnification that will give you the medium steps in power with your telescope, selecting a set of eyepieces that have the apparent fields of view that you desire that will produce the true fields of view that you typically require for the objects that you observe. And then you need to consider a set of eyepieces that have enough eye relief so that you can have the eye comfort that you require. This is how a telescope works: aperture, focal length, f ratio. The telescope focal length divided by the telescope aperture equals f ratio. From here we can determine magnification and true fields of view. So let's discuss focal length. All telescopes and eyepieces have optics polished to focus at a certain distance. This distance between the lens and the focused image, usually measured in millimeters, is called focal length. A longer focal length lens produces a narrower field of view, and a shorter focal length lens produces a wider field of view. So how does magnification work? The focused image from the telescope lens is being magnified by the eyepiece. In this case, the telescope focal length is about 160 millimeters, and the eyepiece is only 20 millimeters, producing 8 times magnification. This is how we calculate magnification. What you do is you take the telescope focal length, usually in millimeters, divided by the eyepiece focal length, also in millimeters, and that will equal magnification. Or you can take the telescope aperture in millimeters and divide it by the exit pupil in millimeters, and that will also equal the magnification. Now we'll discuss exit pupil. Every telescope and eyepiece combination will produce an exit pupil. It's the focus beam of light where the image is viewed. The diameter of the exit pupil changes with magnification. Lower magnifications produce a larger exit pupil, giving a brighter image. Higher magnifications produce a smaller exit pupil with less image brightness. This is the formula for calculating exit pupil. You take the eyepiece focal length in millimeters and you divide it by the telescope f ratio, and that will give you the exit pupil number. Or you can take the telescope aperture in millimeters and divide it by magnification, and this will also give you the exit pupil number. Both of these numbers will end up being in millimeters. Observing faint objects. Telescopes are light-gathering devices capable of focusing images of objects at incredible distances. Under dark skies and the right telescope and eyepiece combination, it's possible to visually observe faint galaxies that are many millions of light years away. Of course, with more light to your eye, you can see the faintest details of every object you look at. But to see the faintest details, you need to be comfortable and observe at the lowest useful magnification. In order to see the faintest and the most distant celestial objects possible through your telescope, you need to find the eyepiece focal length that will produce an exit pupil that will closely match the entrance pupil of your fully dilated eye when dark adapted. For young people, it's not unusual for pupils to dilate to 7 millimeters or more. Older people may have pupils that can only dilate to 5 millimeters. So visit your eye doctor to have your fully dilated pupils accurately measured. With this information, you can choose the perfect lowest power eyepiece. Now, for determining lowest useful magnification power, try to determine which eyepiece on your telescope will produce an exit pupil that comes closest to matching your fully dilated eye. If you select an eyepiece that produces a larger exit pupil than what your eye can dilate to, then you're not able to experience the full brightness of the focused image. It's important to calculate the eyepiece focal length for lowest useful magnification. Here's a useful formula for calculating the eyepiece focal length for lowest useful magnification. What you do is you take the telescope aperture in millimeters and you divide it by the fully dilated eye in millimeters. That will give you lowest useful magnification. Then take the telescope focal length in millimeters and divide it by the lowest useful magnification number. That'll tell you which eyepiece focal length you need. Another typical way to find lowest useful magnification is to use the rule of thumb of 3.5 power per inch of aperture. With a 102 millimeter lens, a 4-inch aperture telescope, the lowest useful magnification is 14 times. But what about high power observing? Telescopes are also detail resolving devices capable of focusing highly detailed images of objects. Under steady skies called good or perfect seeing conditions and the right telescope and eyepiece, it's possible to visually observe incredibly fine features of bright objects like the planets and the moon. But there's a limit to how much magnification you can use, and that limitation will be based on the atmospheric seeing conditions and the telescope's aperture. Having several eyepiece focal lengths from lowest useful magnification to highest useful magnification will maximize your observing potential. Atmospheric seeing and the Pickering scale. The atmosphere can be very turbulent, called bad seeing, to perfectly calm, called perfect seeing. Turbulence in the air causes stars to scintillate or twinkle. Viewing conditions with bad seeing, 1 to 4 on the Pickering scale, distort images of stars, planets, and even the moon. This distortion looks much worse with larger aperture and higher magnification. Viewing conditions with good to perfect seeing, which would be 7 to 10 on the Pickering scale, allows telescopes to be used at higher magnifications, which will reveal fine details on every object you observe. The Pickering scale shows 1 is the worst seeing with 5 arcseconds or more star blur at the sharpest focus, and 10 is perfect with 0.5 arcseconds or less. Average nights of seeing would range from 5 to 7 on the Pickering scale. To determine highest useful magnification on any given telescope, determine the telescope's aperture in millimeters and multiply that number by 3. With this 102 millimeter refractor, the result is 306 power. So how do you calculate the eyepiece focal length for highest useful magnification? So this formula is for calculating the eyepiece focal length for the highest useful magnification. What you do is you take the telescope aperture in millimeters, multiply by 3, and that'll give you the highest useful magnification number. Or a more conservative number could be brought about by taking the telescope aperture in inches, multiplying it by 60, or if your seeing conditions are not that great, maybe by 50, and that would give you the new highest useful magnification number. Then you take the telescope focal length in millimeters and you divide it by the highest useful magnification number. That will give you the eyepiece focal length that you need to get. What's aperture masking and how can it improve your high power observing? During times of poor to bad seeing, images of the moon, planets, and double stars observed at higher power can be improved by reducing the entrance aperture of your telescope. Masks can be made from various sizes from cardboard. With less aperture, there is less resolving power, but images will look sharper. Now that you understand lowest useful magnification and highest useful magnification, you need to calculate the medium steps in power so that you can get the best observing potential possible. Many astronomers own several eyepieces that range from lowest to highest power for their telescope. Medium power eyepieces are also selected by magnification, apparent field of view, and eye relief. Many astronomers begin their observations at low or lowest power and then gradually increase power until the object is best seen. What are eyepiece multipliers? Increasing magnification of your lower power eyepieces can also be done by adding focal extenders or a Barlow lens to your eyepieces. The advantage is that these devices can increase the magnification of all your eyepieces, but the eye relief will remain unaffected. This is especially useful if you need long eye relief of your long focal length eyepiece, but you want more magnification. Many people want to know what's the difference between apparent field of view and true field of view. True field of view is the actual degrees of sky coverage that you're looking at, the chunk of sky that you see. But apparent field of view is the angle of degrees from your eye to the edge of the field stop in the eyepiece. When you're looking through an eyepiece that has wider apparent field of view, you not only get more true field of view, but you get this effect that you're seeing through a wide picture window. More apparent field of view gives you more true field of view. The Orion Nebula M42 is 60 arc minutes by 66 arc minutes in angular size, or twice the size of the full moon in the sky. This is M42 with a telescope of 714 millimeters of focal length and a 68 degree 20 millimeter eyepiece. This gives you 35.7 power, and it will also produce a 1.9 degree true field of view. Then in this other image, we've got M42 with a telescope of the same focal length, 714 millimeters, and the same focal length of eyepiece of 20 millimeters. So we're getting the same magnification of 35.7 power. But with 100 degree apparent field of view, we're getting 2.8 degrees true field of view. You actually see more area around the object, but at the same magnification. So how do you calculate true field of view? You take the eyepiece apparent field of view and you divide it by magnification, and that will equal true field of view in degrees. Or another way of doing this is take the eyepiece field stop. You can get that from the manufacturer. You divide it by the telescope focal length in millimeters, and you multiply it by 57.3, and that will also give you the true field of view number in degrees. You have to relax to see more, and this is the importance of eye relief. Eye relief is the distance from the last surface of an eyepiece of which the observer's eye can see the full viewing angle. If the observer's eye is outside of this distance, then the observer will not see the full viewing angle. Long eye relief eyepieces give more eye comfort, and if long enough, 18 millimeters or more, will allow observers to wear glasses when observing. That's usually needed for someone that has astigmatism in their eyes. Generally speaking, short focal length, higher power eyepieces have less eye relief than long focal length, lower power eyepieces. Eye relief distance information is provided by the manufacturer. You love to observe deep sky objects, but what about light pollution? Just because you're not under the best dark sky sight doesn't mean that you can't still observe some bright galaxies, star clusters, and nebula. Improving your skills as an astronomer has a lot to do with how often you observe, even if that means you do most of your observing near city lights. To improve the view of deep sky objects under light-polluted skies, you can use moderate increases in magnification, which will make the background sky look darker. There are also special filters that you can use with your eyepieces that can increase contrast. To judge the quality of your sight, you can use the Bordel Scale. You can have the darkest skies possible, but also not see very many stars, and that has to do with atmospheric transparency. The Bordel Scale is a 9-level numeric scale that measures the night sky's brightness of a particular location. It quantifies the astronomical observability of celestial objects and the interference caused by light pollution. Class 9 on the Bordel Scale is the most light polluted sky, where you can barely see any stars in the sky at all. When you go all the way down to Class 1, you're now under perfectly dark sky conditions, where the sky's black to the horizon. But there's another aspect that's very important to astronomers, and that is sky transparency and atmospheric extinction. It's possible to be under a dark sky, but not to be able to see many stars due to poor sky transparency or atmospheric extinction. Generally speaking, the very best dark sky sites are far away from city lights, you're up high in elevation with smooth terrain, and the sky has very little water vapor or aerosols in the atmosphere. You can learn more about sky transparency and atmospheric extinction at this website. So to sum it up, by choosing the right eyepieces, you're going to have the most relaxing, most detailed observations you can possibly make. The more comfortable you are and the longer you look, the more you see. Long eye relief eyepieces with large apparent field characteristics allow you to relax more at the eyepiece by letting you back away from the optics while allowing your eye to comfortably scan the field of view in order to use averted vision. A relaxed eye observing at any magnification that's not staring at the object can see fainter details and finer structure than a strained eye. So happy observing. So I hope all you guys enjoyed that and found it informative. I was answering some of the comments on, through live chat. It's great to hear that some of you are watching from around the world. This next little clip that I have here is with Jack Newton. Jack Newton is he's a great friend of mine, but he's someone that's done tons of observing. He is a pioneer of film astrophotography and CCD color astrophotography, being one of the first guys to have actually done it. He still plugs away almost every clear night doing supernova research and asteroid work, and he was also someone that did some incredible solar stuff. He operates an astronomy bed and breakfast in Canada, which you can still attend up there in Soyuz, Canada. Here's a few moments with Jack Newton.
They want to find out who the guy is.
Yeah.
They put him in there.
Right.
And that's what I look like right now, but I'm alive.
You're still alive. You're very alive, okay?
Very alive.
So, anyways, this is Jack Newton. We're at the Soyuz Observatory B&B, okay? And Jack has been trying to get me to come up here for 20 years.
Yes, and he finally arrived.
Finally arrived, and here we are. And of course, this is the 16-inch LX200 telescope that he's done all these famous images with. There's a Coronado 90 that's on here. He is world famous for his solar images. He is a pioneer of astrophotography, CCD color imaging. He's written tons of books, given zillions of lectures, and he's known all over the world. And we're talking now about he's got an Explorer Scientific 9mm 120 degree apparent field eyepiece on there.
And it's absolutely phenomenal. 3 nights ago we had subarc second seeing on Saturn, and we could trace Cassini's division right through the little bitty thin part and all the way around.
Wow.
And the color was unbelievable. You could see the yellow tints and the bands on Saturn. And that wind shear is like 1,100 miles an hour. And the guests, it just absolutely blew them away. They've never seen anything. And what I really like of it, although I'm too old to take the whole field of view in at one crack, is that when you throw it onto Saturn under that kind of power, this is over 400 power, it wasn't quite in the middle. But by tipping your eye, you can spot it off on the edge.
Off on the edge, right?
It's so wide.
Yeah, and you don't have to move the scope, right?
You center the telescope and bingo.
Yeah,
it's dead center.
Yeah. See, that's not even something I would have even really talked about. That 120 degree apparent field was I did it because I wanted to get something that was theoretically the widest field of view possible. But you're right. There's some people that can't see
Well,
the
yeah,
whole thing.
I'm 74 years old, and my eye won't too, but I would buy that in a heartbeat just because of the fact that even though it's got a bigger field of view than
You can
what
just
I'm capable
look.
of, I can look off to the side and recenter an object like a planet, and there's a lot of younger people, of course, that are looking through that same eyepiece and take advantage of it. But what a sweetheart! That
Thanks. Thank you.
Top notch.
Thanks.
Well done.
So, anyways, it was nice spending a few minutes with you guys today. Hazari was mentioning I should probably do a video on how to clean and maintain telescopes. He lives in an area where there's a lot of humidity, and that's a big problem in a lot of places in the world. And humidity definitely is the enemy of optics. That is the reason why we make waterproof eyepieces so they don't fog up on the inside. You can rinse them, you can put them underwater. Sometimes I demonstrate our eyepieces actually in a bowl of water. I pull them out and clean them off and stuff like that. And the eyepieces are still pristine on the inside. And they're guaranteed to be waterproof. So anyhow, I will be back with other videos and other information to share with you guys, and I'm glad that you guys shared this this astronomy day with me. And if it's clear wherever you are, get out with your scope and observe in the backyard or wherever you can. I know that we're all going through this coronavirus thing, but we can still observe the universe as far as we can see. So take care and thanks very much. Bye-bye.